Uh, Imagine this. You're heating on a piece of metal.
Mm-hmm.
It starts to glow, right? First red,
Yeah.
then orange, and then eventually it gets white hot.
Hmm.
We see this all the time.
Yeah.
But over a century ago,
Mm-hmm.
this seemingly simple thing, I mean, it really sent physicists into a tailspin.
Into a tailspin.
It's called the Ultraviolet Catastrophe.
Yeah.
And no, it's not some sci-fi disaster movie or anything.
Right. What's so fascinating about the ultraviolet catastrophe is that it exposed this huge crack in the foundation of classical physics.
Oh, wow.
Back then, physicists thought they had the universe pretty much figured out, with Newton's laws and Maxwell's equations.
They thought they had it all, huh?
They really did. But this one little problem just showed them how much they didn't know.
So it wasn't a real catastrophe,
No.
more like a scientific meltdown.
Exactly. It was a theoretical catastrophe.
Okay.
You see, classical physics predicted that as an object heats up, it should release an infinite amount of energy, particularly in the ultraviolet part of the spectrum.
Hold on, infinite energy.
Yeah.
Wouldn't that mean that everything would be constantly exploding?
Yeah.
Like with the power of 1,000 suns.
That's the problem.
Yes.
Obviously, that's not what happens in reality.
Yeah.
And that discrepancy between the theory and observation, that was the catastrophe.
Yeah, okay.
It meant our understanding of light and energy was fundamentally flawed at a very basic level.
That's kind of mind-blowing.
It is.
So we're diving into this ultraviolet catastrophe today.
We are.
And I see we have a ton of sources here.
We do.
FAQs, timelines, study guides.
Yeah.
Even a final podcast episode.
Oh, wow.
I'm already feeling a bit overwhelmed.
Yeah.
But excited to see where this goes.
Well, don't worry. We'll break it down.
Okay.
To really understand this.
Yeah.
We need to kind of step back in time. Okay.
To the late 19th century.
Right.
When physicists were grappling with something called blackbody radiation.
Blackbody radiation.
Yeah.
That sounds kind of ominous.
Yeah.
Is it like some kind of dark matter situation?
Not quite. Think of a blackbody as this idealized object that absorbs all light that hits it, regardless of the wavelengths.
Okay.
And then it emits radiation based solely on its temperature.
Okay, so it's like the ultimate light sponge.
Exactly.
And then it glows depending on how hot it is.
Exactly. And physicists at the time wanted to figure out how to predict the exact spectrum of light emitted by a blackbody at different temperatures.
Good.
They wanted a formula, a way to calculate it precisely.
So it's like they were trying to crack the code of how things glow when they get hot.
Exactly.
I can see how that would be important.
Absolutely. And they came up with a formula called the Rayleigh-Jeans law.
Using the principles of classical physics.
Right.
And for long wavelengths, like infrared light, it worked quite well.
Okay.
But as they moved towards shorter wavelengths, like ultraviolet, that's where the trouble began.
This is where it gets interesting, right?
Yeah.
Because their neat little formula started predicting some pretty wild stuff.
It did. It predicted that the energy emitted by a blackbody would increase infinitely as the wavelengths got shorter and shorter. In other words, the hotter the object, the more ultraviolet light it would emit, leading to, infinite energy.
So their calculations were basically saying that a hot stove burner should be able to vaporize an entire city.
Yeah.
That's a bit of a problem.
And it's putting it mildly.
Yeah.
This was the ultraviolet catastrophe in a nutshell.
Okay.
A complete breakdown of classical physics in the face of experimental evidence.
So what happened next? Did they just throw out their hands and say, physics is broken?
Well, not quite.
Okay.
There was a lot of head scratching and debate.
Right.
And then along came a physicist named Max Planck.
Okay.
Who had this radical idea that would change the course of physics forever.
This is where things get quantum, right?
Yeah.
I've heard of Planck. But I'm still a little fuzzy on what exactly he did.
Well, he proposed that energy wasn't continuous.
Okay.
Like a smooth ramp, that you could climb up or down gradually.
Right.
Instead, he said energy came in discrete packets.
Okay.
Like tiny bundles, which he called quanta.
So instead of a ramp, it's like a staircase.
Yes.
With specific steps you can take. You can't just stand between two steps.
That's a great analogy.
Okay.
And to describe this, Planck came up with an equation.
Okay.
E equals h nu,
All right.
where E is energy and nu is frequency, which relates to wavelength, and h is a tiny, tiny number, now known as Planck's constant.
Okay, so what does this quantized energy have to do with the ultraviolet catastrophe?
Well, Planck's idea essentially put a limit on how much energy could be emitted at very high frequencies, like ultraviolet light, because the energy could only come in these specific packets.
Right.
The infinite energy predicted by the old theory was no longer possible.
So Planck essentially rewrote the rules of the game.
He did.
By saying energy comes in these tiny indivisible chunks.
Exactly.
It's kind of like saying you can't have half a penny.
Right.
You can only have whole pennies.
A perfect analogy.
That makes sense.
Yeah.
So by introducing this idea of quantized energy, Planck essentially put a cap on how much energy could be emitted at those high frequencies, preventing the whole infinite energy meltdown.
Exactly. And what's even more remarkable is Planck's solution wasn't just a mathematical trick.
Okay.
It was a profound shift in our understanding of how energy behaves.
At the most fundamental level.
At the most fundamental level.
I can imagine that physicists at the time, they were probably both excited and a bit terrified by this new concept.
Absolutely. It took a while for the full implications of Planck's idea to really sink in.
Yeah.
In fact, even Planck himself was initially hesitant.
Really?
About the radical nature of his own proposal.
Wow. I guess it's not every day that you stumble upon a discovery that completely rewrites the laws of physics.
That's true.
Like finding out that gravity only works on Tuesdays.
Yeah.
Or something.
But as with any groundbreaking scientific discovery, there was resistance and skepticism at first.
Sure.
But eventually the evidence for quantized energy became overwhelming.
Yeah.
And it opened up this whole new realm of physics.
Okay.
Quantum mechanics.
And quantum mechanics is kind of a big deal, right?
It's a huge deal.
Yeah.
It's like the rule book for how the universe works at the subatomic level.
Right.
And it's led to some pretty mind-blowing technologies.
So this seemingly abstract problem about blackbody radiation ended up having very real consequences.
It did.
For our everyday lives.
Absolutely.
Wow.
And the impact of quantum mechanics goes even beyond technology.
Okay.
It's also reshaped our understanding of the nature of reality itself.
What do you mean?
Well, for example, in the quantum world, particles can exist in multiple states at once.
Oh, wow.
And things don't behave in this neat, predictable way that we're used to in the macroscopic world.
Yeah, it's almost like the quantum world operates on a completely different set of rules.
Yes.
Which is kind of unsettling and fascinating at the same time.
Absolutely. And it's important to remember that this revolution in our understanding of the universe stemmed from this one seemingly simple question.
Okay.
How do hot objects glow?
It really shows how science is all about asking questions.
Yes.
Even seemingly mundane ones.
Right.
And then following the evidence wherever it leads.
That's what science is all about.
Even if it leads to a complete overhaul of our understanding of reality.
Exactly. It's a testament to the power of curiosity and the scientific method. And the ultraviolet catastrophe is a perfect example of how a crisis in physics can lead to these profound breakthroughs that shape not just our understanding of the universe, but also our technological capabilities.
So we've gone from hot glowing metal to the mind-bending world of quantum mechanics.
We have.
It's amazing how one seemingly simple problem could unravel so much of what we thought we knew.
And what's even more remarkable is we're still uncovering the full implications of quantum mechanics today.
Wow.
There are still so many mysteries to be solved.
Right.
And who knows what other technological revolutions await us as we delve deeper
into this strange
and wonderful world.
That's what makes science so exciting.
I agree.
It's not about having all the answers. It's about the constant pursuit of knowledge.
Yes.
And the willingness to challenge our assumptions.
Yeah.
Even when it feels like the universe is trying to tell us something completely bonkers.
I couldn't agree more. The ultraviolet catastrophe is a reminder that the universe is full of surprises and that even our most cherished scientific theories can be overturned when confronted with new evidence.
So, dear listener,
yes,
what does this all mean for you?
It means that the world is a much stranger and more wondrous place than we might imagine. And it highlights the importance of staying curious, asking questions, and embracing the unknown.
Right.
Who knows? Maybe you'll be the one to make the next groundbreaking discovery that changes our understanding of the universe.
It's inspiring to think that we're still just scratching the surface of quantum mechanics.
Absolutely.
Who knows what other mysteries will unravel in the years to come.
And it makes you wonder what other seemingly settled science might be waiting for its own ultraviolet catastrophe moment.
Right. What other assumptions might we be holding on to that will eventually be overturned by new discoveries?
It's a
humbling thought,
yeah,
but also incredibly exciting.
It is. It really underscores the importance of staying open-minded and questioning everything, even the things we think we know for sure.
Well, I think we've given our listeners
I think so.
a pretty good deep dive into the ultraviolet catastrophe.
We did.
And the wild world of quantum mechanics.
A very wild world.
What are your final thoughts on all this?
I think the biggest takeaway is that the universe is constantly challenging us to expand our understanding.
Right.
The ultraviolet catastrophe.
Yeah.
It wasn't just a scientific problem to be solved. It was a doorway into a whole new way of seeing reality.
So to our listeners out there,
yes,
if you're fascinated by the strangeness of the universe and the power of scientific discovery, keep exploring.
That's right.
There's a whole universe of knowledge out there waiting to be uncovered.
And who knows?
Yeah.
Maybe you'll be the one to stumble upon the next catastrophe that leads to an even greater revolution in our understanding of the cosmos.
That's a great note to end on. Thanks for joining us.
Thank you for having me
on this wild ride through the ultraviolet catastrophe.
It was my pleasure.
Until next time.
Yes.
Keep those minds curious.
Stay curious.
And those questions coming.
Keep asking questions.